In this series of videos, we're going to look at how the principles of dynamic equilibrium apply to acid-base reactions, starting with a little bit of a review about what exactly makes acids and bases what they are. So as you learned in Chemistry 11, the Bronsted-Lowry acid-base theory relies on the transfer of H plus ions from acids to bases. So Bronsted-Lowry acids, such as acetic acid here, are what we call proton donors because once they are put into water, they give up or donate an H plus. So if we look at the mechanism behind this, we know that because of an acid's polarity, the lone hydrogen on the COOH group has quite a strong positive pole, which can attract one of the lone pairs on water to form a bond with it and cause the bond between hydrogen and oxygen to break, becoming a lone pair on the oxygen like this. So if we draw what the products are going to be, remember that when water takes one of the hydrogens from the acid, it's going to end up with only one lone pair, an extra hydrogen, and consequently the oxygen is going to have a positive charge on it, and this of course is the hydronium ion, which is produced in pretty much every Bronsted-Lowry acid reaction. Now, the acid, on the other hand, is going to be missing the H+, so the left side of the molecule is not affected because it doesn't contain the acid functional group, but because the acid functional group is missing its hydrogen, now the oxygen that has a single bond with carbon has three lone pairs like this and a negative charge. Now, the reason why we can apply the principle of dynamic equilibrium to this particular acidic reaction is because this reaction is reversible. So if we actually want to go back to the reactants, we can take one of the lone pairs on the negatively charged oxygen in acetate and use that to reform the bond with the extra hydrogen on hydronium, breaking that bond and turning it into a lone pair, which would give us back water and acetic acid. So because of the fact that this reaction is reversible, we can actually write a KEQ expression for this reaction. So our reactants would be our acid CH3COOH plus water, and our products would be CH3COO minus, the acetate ion, and hydronium. Now, once we have our equilibrium expression, we can actually write a KEQ equation for this as well, where we take the concentrations of our products, so the concentration of the acetate ion times the concentration of the hydronium ion. Now, remember that we're not going to write water on the denominator here because water is a liquid and the concentration of liquids is defined as constant since there are no other liquids in this reaction. So the only thing that appears in the denominator is the concentration of acetic acid. And as a consequence of this, just like how we use a different spelling of KEQ for solubility equilibrium, because this is an acid equilibrium, we can refer to this by the equilibrium constant Ka, A of course referring to the fact that this is an acid ionization. Now, conversely, if we consider ammonia, probably the most well-known Bronsted-Lowry base, we call ammonia a base because it's what we call a proton acceptor, meaning that when we put ammonia into water, it's going to use its lone pair to pull a hydrogen off of water and break this bond, turning it into a lone pair. So we can see from this mechanism that ammonia is gaining an H plus in water, and if we draw what the products are going to be, we would end up with ammonia with no lone pair and an extra hydrogen, also known as ammonium, and because the nitrogen here is losing its electrons in favor of forming a bond, it's going to have a positive charge, and we can see that ammonia is acting as a base because even though it doesn't contain OH minus in the structure, when it reacts with water, it produces OH minus as a byproduct here. Now, just like with the acetic acid reaction, this reaction is reversible, which means that one of the lone pairs on hydroxide can reform a bond with the extra hydrogen on ammonium, break the bond, and have it turn back into ammonia, which means just like with acetic acid, we can write a dynamic equilibrium reaction where we have as our reactants ammonia reacting with water, and then as our products we would have ammonium with a positive charge and the hydroxide ion like this. Now again, because we've got an equilibrium reaction here, we can express this as a KEQ expression where we take our concentration of products, concentration of ammonia times the concentration of OH minus, and again, water doesn't appear in the denominator because it's acting as a pure liquid. It is the only solvent within this reaction, so the only concentration that goes in the denominator is the concentration of NH3. Now, just like how an acid ionization, we call the equilibrium constant Ka, because this is a base ionization, we would call the equilibrium constant Kb instead. Now, the most important thing to note about acid-base equilibrium reactions, and because the reaction is reversible, because these reactions are reversible, the acid or base in the ionization does not ionize completely. What that means is that 100% of the ammonia or 100% of the acetic acid is not going to react with water, because some of which is going to undergo the reverse reaction and turn back into the reactants. Therefore, because these acid and bases do not ionize completely, these are what we call weak acids and bases, unlike strong acids and bases like, for example, HCl and NaOH are strong acids and bases. Strong acids and bases do ionize completely and therefore do not have a reverse reaction and do not form equilibrium situations. Another thing to keep in mind with acid-base ionizations is that acid and base ionizations of weak acids happen 1H plus at a time. So if we consider an acid that has more than 1H plus, like carbonic acid, for example, each of its ionizations is considered as a separate reaction, and therefore each of them is going to have a different equilibrium reaction and a different Ka expression as a consequence. We can see these by actually drawing the mechanism. So in this case, water is going to break the bond that hydrogen has with the oxygen on the left side of carbonic acid, and we're going to end up with hydrogen carbonate as the byproduct of what happens when carbonic acid loses its H+, and we're going to end up with hydronium because, again, water is taking this hydrogen here. Now, because hydrogen carbonate has a second hydrogen here, there is technically a second acid ionization reaction that can happen like this, where water again uses its lone pair to form a bond with this hydrogen and break this bond between hydrogen and oxygen, turning it into a lone pair, which gives us, at this point, because our carbonate has no hydrogens bonded to it, we would actually end up with the carbonate ion with a negative charge on each of the oxygens, so we would just write this as CO3 2-, and we would end up with a second hydronium molecule that we've made because there are two ionizations that are possible. So from this, we can see that even though there are some acids that can lose multiple hydrogens, each time an acid loses a hydrogen, it is treated as a separate ionization reaction because, again, if we were to write a KEQ expression, or rather a Ka expression, the second ionization and the first ionization would have different Ka expressions. And for that reason, these ionizations are considered separate. So to conclude the video, we can put terminology to acids and bases depending on the number of H plus ions they lose or gain. So for example, nitric acid only has one H plus ion that it can lose, which means that we would call it a monoprotic, simply meaning one proton acid, while carbonic acid, the acid that we just saw, has two H plus ions that it can lose, so we would call it a diprotic acid. Now, you can probably see what's coming here. Phosphoric acid has three possible H plus ions that it can lose, so it is what we call a triprotic acid, and generally any acid that has more than three H plus ions that it can lose are what we call polyprotic acids. And as a practice problem that you can try before the next video, you can take a look at a rather extreme example of a polyprotic acid, pyrophosphoric acid, which is the acid that's formed when you have the polyatomic ion of two phosphates stuck together. So before the next video where we go in depth, a little bit more in depth with compounds that can behave as both acids and bases, see if you can answer these questions about pyrophosphoric acid.